In this module, we are going to see several examples. This is in some sense the most important example. As the popular saying goes, an example is worth 1,000 proofs. So let's start the first example. The constant sequence an equal to k converges to k. Well, there is really nothing to prove. For the choice of n epsilon, you can choose any natural number. This will work. Okay. The second one we have already seen, 1 by n converges to 0. This is an example that we saw in some detail. Now, 3. 1 by n squared converges to 0. 1 by square root of n converges to 0. Okay. Now, how do you show this? Well, there are two ways. One of them is the clever way. The other one is the way that you shouldn't even be considering. Let's do it the clever way. Okay, the clever way is as follows. Suppose n of epsilon is the function coming from 1 by n converging to 0. Since 1 by n converges to 0, there is a function n of epsilon that does what is needed in the definition of the definition of convergence. Now, choose the same n epsilon for showing 1 by n squared goes to 0. The same will work. Why will the same work? Because 1 by n squared is less than 1 by n. That's the reason. So the same n of epsilon will work. Okay. What about for 1 by square root of n? Well, just choose n of epsilon square. Okay. Choose n of epsilon square. How does this help? If 1 by n is less than epsilon, then epsilon square, then 1 by square root n is less than epsilon, right? So if small n is greater than n of epsilon squared, then 1 by n is less than epsilon squared, and therefore 1 by square root of n is less than epsilon, right? So this quickly dispenses off 1 by square root of n also. Just a remark, for this function, for this sequence 1 by n squared, we could have also used the fact that 1 by n converges to 0 and applied the fact that product of sequences, the limit of a product of a sequence is the product of the limits. We could have done that also. Okay. So these are some easy examples. Now let's start seeing some more slightly complicated ones. Okay. 4. 1 plus or minus 1 by n. Okay. 1 plus or minus 1 by n. Well, this converges to 1. Okay, this sequence. Why is that the case? Because 1 by n converges to 0. And we can use the algebraic limit theorems. By algebraic limit theorems. Okay. So the sequence 1 plus or minus 1 by n converges to 1. This is not really complicated. I did not keep up my promise. Well, no worries. Look at this one. Sin n by n. Now, this looks complicated, but at first sight you might think, well, why not I just apply the fact that quotients, if you have an by bn, then the limit is just a by b, where an converges to a and bn converges to b. Well, this is slightly problematic because the denominator sequence n certainly doesn't converge, it diverges to infinity. And the numerator sequence, look at sine n, sine 1, sine 2, sine 3, sine 4 and so on. If you were to plot this, you will notice that this oscillates wildly. So it isn't really clear what I'm supposed to do with this. Well, let's manipulate first. Sin n by n, let's look at mod of sin n by n, because at the end of the day, if this were to have a limit, I would guess it is 0, because the denominator as the term n and 1 by n goes to 0, I would guess that this also converges to 0. Look at mod sin n by n. Okay. Now all of us are familiar with the fact that minus 1 less than or equal to sin x less than or equal to 1 for all x in R. Okay. This comes from the definitions, the various basic properties of the sine function. We will rigorously define what the sine function, the cosine function, the logarithm, exponential in a later module. But for the time being, you can just take this for granted. You have known this all the way back from 8th or 9th standard. So minus 1 is less than or equal to sin x is less than or equal to 1 for all x in R. Okay. So certainly this is going to be less than or equal to 1 by n. Right? This is certainly going to be less than or equal to 1 by n. Well, in fact, what is this saying? This is just saying minus 1 by n less than or equal to sin n by n less than or equal to 1 by n. Okay. Now apply the squeeze theorem. Apply the squeeze theorem. Both the RHS sequence 1 by n converges to 0, the LHS sequence minus 1 by n converges to 0, therefore sin n by n has to converge to 0. Apply the squeeze theorem to conclude sin n by n converges to 0. Okay, so this was a somewhat involved example. Now let's see some more. What I'm going to do now is consider the sequence a power n. Note, this is not a power n. So what I'm going to do is, to make it ultra precise, consider the sequence b power n, where b is fixed. Okay. Now what happens to this sequence? Well, it depends on whether the modulus of b is greater than 1 or the modulus of b is not greater than 1, that is, it lies between minus 1 and 1. Okay. To see this precisely what happens, what we will do is, first we will consider b greater than 1. The case b equal to 1 is the simplest. It's just going to be 1, 1, 1, 1, 1. It converges to 1. Consider the case b greater than 1. What I do is write b as 1 plus r, where r is greater than 0. I can do this because I'm assuming b is greater than 1. Okay. Now I want to compute 1 plus r power n. Right? That's the nth term of this sequence. How do you compute this? Well, we know the familiar binomial formula. If you're not familiar with this, just check your high school textbooks again. You would have proved it using induction or by a combinatorial argument. Okay. Now what is this? This is nothing but 1 plus nr plus dot 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 some other terms plus r power n. I'm not really interested in the in-between terms. They will involve the various n, choose something. I'm not really interested in those terms. But the key fact is all these terms are positive. All these terms are positive. So in any case, 1 plus r power n is greater than or equal to 1 plus nr. I'm just ignoring all the other positive terms. So 1 plus r power n is certainly greater than or equal to 1 plus nr. Right? But now r is a fixed quantity. This is a fixed quantity. That means when I multiply n with r, we see that nr diverges to infinity. Please recall the definition of what diverges to infinity means. Diverges to plus infinity, to be ultra precise. This just means that nr can be made larger than any pre-specified number if n is large enough. Okay, in fact, you can precisely write down how large small n has to be for nr to be greater than some capital M in terms of small r. That is easy to do. Okay, so what this shows is 1 plus r power n also diverges to plus infinity. Also diverges to plus infinity. Okay. Now, we have dealt with the case when this number b is greater than 1. Now choose b such that 0 is less than or equal to b is less than 1. Okay. Now, how do you deal with this case? You might be tempted to write b as 1 minus r and take 1 minus r power n. Well, don't do that. Always try to use what has been shown so far. Let c be equal to 1 by b. Okay. Let c by definition be equal to 1 by b. Well, of course, if b is not 0, whenever b is not 0. Again, the case b equal to 0 is really trivial. I'm not going to leave that to you. There's nothing really to show. I will just take 0 less than b less than 1. So take c to be 1 by b. Now what happens? 1 by b power n, or in other words, c power n diverges to plus infinity. Why? Because c greater than 1. Because c is greater than 1, and that's the case we immediately just saw. Okay, because c power n diverges to plus infinity and c power n is 1 by b, this means that if n is chosen, not n, okay, let me write down a full proof. Fix epsilon greater than 0, let capital M be 1 by epsilon. Okay, then we can find n epsilon such that if small n is greater than n epsilon, then c power n is greater than 1 by epsilon. Okay, but this is same as saying 1 by b power n is greater than 1 by epsilon, which is same as saying b power n is less than epsilon. Okay, so this shows b power n converges to 0. Okay, let me summarize what is it that we have shown. We have shown that if b is greater than 1, then b power n diverges to plus infinity. If 0 less than or equal to b less than 1, then b power n converges 0. Okay, now if minus 1 less than greater than b less than or equal to 0, then b power n again converges to 0. Why is this? Well, I'm going to leave it to you. Exercise. Okay, excellent. This is a very interesting one. So we have now shown that the sequence b power n, the behavior crucially depends on the choice of b. Okay, next example, 7th one. For this one, let me choose a somewhat complicated example. Let again, let me just deal with the case 0 less than b less than 1. Let 0 less than b less than 1 and define an to be 1 plus b squared plus dot 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 b power n. Okay. I'm defining the nth term of the sequence to be just 1 plus b squared plus dot 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 b power n. Okay. What is limit of an as n goes to infinity? All of you know the answer. It's just 1 by 1 minus b. This is called the geometric series. 1 plus b squared plus dot 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 so on all the way up to infinity is called the geometric series. So this geometric series will serve as a motivation. In fact, this was related to what we saw in that story about chocolate wrappers. So this series converges to 1 by 1 minus b. How do you show that? Well, it's rather easy. You just have to use a bit of algebra. The bit of algebra is as follows. 1 plus b plus dot 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 b power n. I can write this as 1 minus b into, so I need a 1, so I put 1 here. I need a b, so I put plus b here. Okay, plus b squared plus dot 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 b power n minus 1. Okay, is this no, I made a slight mistake. What I want to say is 1 plus 1 minus b power n plus 1 is actually equal to 1 minus b into 1 plus b squared plus dot 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 b power n minus 1. In fact, this is all the way up to b power n. Why is this correct? Well, there is a 1 accounted for by 1 into 1. Okay. Then this minus b power n plus 1 is accounted for by this product. What happens is all the intermediate terms, b comes once as positive and once negative. B squared comes once as positive and once negative. Everything else just cancels off. So 1 minus b power n plus 1 is actually equal to 1 minus b into 1 plus b squared plus dot 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 b power n. So what we are interested in, a power n is nothing but 1 minus b power n plus 1 by 1 minus b. Right? Now if you were to observe this identity, this algebraic identity is true whenever b is not 0. Whenever b is not 0, this is true. So we have got an equal to 1 minus b power n plus 1 divided by 1 minus b. Excellent. How does this help us show what the limit is? Well, 0 is less than b is less than 1. So b power n plus 1 converges to 0. That's what we just saw in the last example, right? So the numerator converges to 1. And the denominator is just the constant 1 minus b. So an converges to 1 by 1 minus b. Okay, excellent. Now what happens if minus 1 less than b less than or equal to 0? Again, I leave it to you as an exercise. Hint, you get exactly the same thing. you get exactly the same thing. So this shows that the geometric series converges to 1 by 1 minus b. Excellent. Now, one more example before we conclude this set of examples. Again, this is going to be a somewhat complicated one. This is example number 8. Okay. What I do is fix x in R and consider 1 by 1 plus n squared x. Okay. Fix a number x in R and consider 1 by 1 plus n squared x. Okay. What do I do with this? We want to show that if x is 0, then 1 by 1 plus n squared x converges to 1. There is nothing to show because this will just become 1 by n. Now, if x is not 0, then 1 by 1 plus n squared x converges to, as you can guess, 0. Why is this the case? Well, because 1 plus n squared x diverges to plus infinity if x is greater than 0. And, well, I am not formally defined what diverges to minus infinity is, but let me just loosely use this. Diverges to minus infinity if x is less than 0. Okay? Because of this, we immediately get that 1 by 1 plus n squared x must converge to 0 if x is any number other than 0. Okay? So this is one set of examples. In the next module, we will see some more set of examples that involve polynomials and exponentials together. This is a course on real analysis. You have just seen the module on examples of convergent and divergent sequences.